In this video, I wanted to talk really quickly about the one-particle states that we defined last time as this, just our creation operator acting on the ground or vacuum state. So we could define two particle states like this, so just two creation operators acting on the vacuum state. And we could define, one, if we have two creation operators, one with momentum p, one with momentum q, we could define two states, one with one acting first and the other acting second, like this. But then we know all these creation operators commute, so these two states must be the same. And so that's telling us that our state is symmetric under the exchange of particles, and so these particles are bosons. Another thing about this system is the number operator that I defined last time, it commutes with the Hamiltonian. And because of that, so any operator that commutes with the Hamiltonian, it's conserved. So the particle number will be conserved. And then lastly, the angular momentum, if we have a one-particle state associated with momentum 0, so it's just a particle at rest, and we find the angular momentum of that state, we'll get 0. And so the point of all this is that for this theory, we find that the particles are bosons, the particle number is conserved, and that our particles have 0 intrinsic angular momentum. And for theories later on, we'll find that our states will be antisymmetric under the exchange of particles. So those fields will give rise to fermions. And then if we have in our Hamiltonian interaction terms, that will lead to the particle number not being conserved. And so the number operator will no longer be a conserved quantity, or the number of particles will no longer be conserved. And we'll also find states for other theories where the particles, if we create particles with 0 momentum, so that there's 0 orbital angular momentum, we will still find that acting the angular momentum operator on them gives, for example, 1/2. Yeah, we'll see that later on. So our particles of our Klein-Gordon field are kind of just boring 0-spin bosons. So moving on to the normalization of these states. So if we define our ground state to be normalized like this, kind of a reasonable way, our one-particle states, if we do this inner product here, so this is this, and then we can use, to evaluate this, we can use our commutation relation, get this. And then this term will, so it's an annihilation operator acting on the ground state. So this term will give 0. And then this term is just a number, so I can pull it out. And so we find this. And this is similar to the to how we normalize the normalization we used for momentum and position eigenstates in ordinary quantum mechanics. So the states aren't, directly normalizable. But you have this kind of relation. But the problem with this thing is that it's not Lorentz-invariant. So if you have states in one frame that satisfy this normalization, if you go to another frame, they won't satisfy this normalization. And that's an issue, when we're dealing with probabilities and things. The probability won't be conserved between different frames, but obviously physically what happens shouldn't depend on your reference frame. So we need to do something about that. So I'll just walk through David Tong's argument for how we should normalize the states instead of this, which is first this volume element, the 4D volume element, should be Lorentz-invariant. And our particles, the momentum, the energy of the particles is constrained by our relativistic relation here. P0, which is just E, needs to be equal to it is equal to p squared plus m squared. So if I integrate over this volume, I only will have I should only integrate over the energy where this relation is satisfied. But we can rewrite this using the relation for a delta function. So if we want to integrate over p0, then that will be given by basically 1 over the derivative of this with respect to p0 evaluated at the zeros of this. And so the derivative of this is obviously just 2p0. And the 0 of this is when the energy is equal to p squared plus m squared. So this is equivalent to this. And I've used omega p here. So again, p naught or EP or omega p, they're all the same thing, but we've been using omega p here in the past few videos, so I'll just stick with that. And then what you can do is, so if I know this is Lorentz-invariant, then obviously if I multiply by this thing, I will get 1 because, well, it's clear to see how that works out. And I guess the point is, this is Lorentz-invariant. Obviously 1 is Lorentz-invariant. So if I have these two things that are Lorentz-invariant, then this thing must also be Lorentz-invariant. And so that's telling us that instead of just using this delta function, we need to have this omega p out front as well. And I guess the two, they just bring along. So basically that motivates us to define our states with an extra factor of square root of 2 omega p. So this is the notation he uses. You can see, it's just what we had before, only just with this extra factor here. And so that way our normalization thing will become this. And so we just get this factor of 2 omega p, and we know that this thing is Lorentz-invariant. So our normalization is Lorentz-invariant.